More than 1 million phones buzzed for the wrong fault. At 8:10 on June 24, a 5.6 broke ground 5 miles down. It was not under San Francisco. It was under a monastery at the end of Tomkey Road in Upper Redwood Valley. The address is 16201 Tomkey Road. The first ShakeAlert said magnitude 6 on the San Andreas. The updated location said 6.8 miles north of Redwood Valley. Seismologists had a different name for it. They called it the largest quake ever recorded on the Maacama. A fault most Californians have never heard of had just set its own record, and the ground kept moving after the main shock. This was not one line slipping cleanly. What slipped was something else entirely. You will see why a single line cannot explain what happened there, and why the next slip is not where the map ends. The map stops. The ground does not. Hold that location for a second and the strangeness grows. A quiet valley with orchards and scattered houses hit a record break. Yet the warning named a fault 200 miles south. Tomkey Road is a thin ribbon north out of Redwood Valley. It climbs past orchards, fences, and scattered houses tucked into oak. At the top it narrows and turns to dirt near the monastery gate. Abhayagiri sits there at 16201 Tomkey Road. Red roofs, tall trees, silence broken only by bells and dogs. The quake started 5 miles beneath that quiet. The United States Geological Survey timed it at 8:10 a.m. local. The epicenter landed 6.8 miles north of Redwood Valley. That puts it about 5 miles southeast of Willits and just off Highway 101. Depth was about 8 to 9 kilometers. That is shallow enough to hit hard and close enough to feel personal. In town, people describe 30 seconds of strong swaying, then 20 seconds of rolling. One resident sheltered in a doorway and timed it on instinct. Nothing fell at her house. At relatives in Redwood Valley, a toilet cracked and books left shelves. Pictures dropped from walls and kitchens that had not moved in decades. Phones had buzzed seconds earlier with a ShakeAlert for magnitude 6. The ground then corrected the estimate to 5.6. A small difference on paper and a large difference in the rock. The main shock was not alone. Within 6 hours, at least 35 aftershocks over magnitude 1.3 were logged. Most were tiny and felt by no one. One that afternoon reached 2.8 and rattled dishes again. The bigger story was not the count but the context. The Maacama had gone 70 years producing only modest quakes. Since 1954, about 17 earthquakes between magnitude 4 and 5.2 were likely in the vicinity of the fault. That list comes from careful catalog work, not guesswork. The geologist who knows that catalog best is Laurie Danglar. She has spent 4 decades mapping North Coast hazard at Cal Poly Humboldt. After the quake, she said this 5.6 is the largest earthquake in the instrumental period that appears to be on that fault. That means no larger quake on this fault had ever been measured. A fault lesser known to most Californians had just beaten its own record, and it did so north of where new maps had just drawn new lines. Which raises a simple question that is easy to repeat. Where are the rest of the lines? If 17 small quakes in 70 years were the whole story, a record break should not have happened now. Yet it did, and it landed just beyond the last solid line on LiDAR. Most people carry a single line in their head for Northern California hazard. That line is the San Andreas. It does not work that way north of San Francisco Bay. There, the motion between plates splits into 3. Measure the distance and the split becomes concrete. The road from San Francisco to Willits is about 137 miles. To Redwood Valley, it is about 124 miles, roughly 2 hours and 17 minutes of driving. Draw a line from the coast inland and you cross faults in order. The San Andreas runs near and partly offshore to the west. East of it and parallel lies the Maacama. It runs through Sonoma and Mendocino counties, past Santa Rosa, Ukiah, Willits, toward Laytonville. Total length is about 144 kilometers, roughly 90 miles. Some estimates counting every connected strand push it toward 180 kilometers. It trends northwest and moves right lateral, the same sense as the San Andreas. Ground on the west shifts north relative to ground on the east. For decades, it was treated as the northern end of the Hayward-Rogers Creek system, not a separate curiosity. That family tie is why the slip budget matters. If the Hayward can rupture, the Maacama can too, and the plates do not care which name we wrote on the map. The question is how that motion is paid out each year. Plates move every year, whether we feel it or not. Topography sets the deep rate, and instruments catch the shallow creep. Below about 9 kilometers, the Maacama slips about 13.1 millimeters per year. The San Andreas to the west there slips about 21.5 millimeters per year. The Bartlett Springs Fault to the east slips about 7.5. Add them, and you get roughly 42 millimeters a year, an inch and 2/3. That is the plate budget north of San Pablo Bay, split 3 ways. At the surface, the Maacama does something unusual for a major fault. It creeps. In Willits, instruments averaged about 5.7 millimeters per year over 20 years. That is roughly a 1/4 inch per year of steady motion without shaking. You can see it in downtown Willits, where the fault slices southeast to northwest through town. A curb is offset a few millimeters and paint lines jog. One study estimated creep occurs along 80% of the Maacama length. If 80% is sliding a little every day, pressure should not build, or so the simple story goes. For a long time, that safety logic made the Maacama seem quiet by design. The logic is not wrong, it is incomplete. And incomplete is where the hazard hides. The easy story fits the first half of the facts and then stops asking. In that story, the Maacama is a single right lateral fault, about 90 miles long. One patch near Upper Redwood Valley stuck, then slipped 5 miles down and made a 5.6. Aftershocks clustered around the patch, and the largest instrumental record was set. Old lake beds in Little Lake Valley pulled apart as the fault stepped. Pressure ridges rose where bends squeezed the ground up. The picture is tidy, and it even does math nicely. Long-term slip is about 9 millimeters per year on the Hayward-Rogers Creek trend, continuing north. Observed creep in Willits is about 5.7. Subtract, and you get a small deficit that could load a locked patch. A late bill on one line, payable as a 5.6. That explains why only 17 quakes between 4 and 5.2 happened in 70 years. Strain stored slowly and released rarely. End of story, case closed. Except the ground did something else in 2020 that does not fit a single line. A swarm southeast of Willits refused to line up. If the fault were a single knife edge, that swarm should have tracked the knife. It did not. In August 2020, about 10 kilometers southeast of Willits, the ground lit up differently. It started on August 19th with a magnitude 2.9. 9 minutes later, a magnitude 4.2 hit, the largest of that sequence. Over the next 4 months, the activity did not decay like normal aftershocks. It swarmed, bursting then quiet, then bursting again through December. The team that chased every tiny quake used waveform matching, and then relocated them to within meters. It was led by USGS seismologist David Shelley, with colleagues Robert Skumal and Jean Hardebeck. For thousands of quakes smaller than magnitude 1, they measured first motion and the ratio of S to P waves. Then they sorted each quake onto its real fault plane instead of guessing. What came out was not one line. The swarm started on a right lateral strand, plausibly of the Maacama. Then it lit up many left lateral faults at right angles to it, short in echelon cracks. Together, these interlocking faults form a fracture mesh. That phrase is exact from Geophysical Research Letters in 2023. The paper adds consistent with structures associated elsewhere with fluid-induced faulting and earthquake swarms. Water under pressure pries open tiny cracks and slip on one loads the next. The map did not show a line after that work. It showed a cloud about 1 kilometer across. That cloud sits inside a broader zone 10 to 20 kilometers wide that follows the Maacama trend but is not a knife edge. Picture a kitchen scrubber, not a string. Pull one corner and many fibers move. Some stretch, some cross fibers snap. The whole shape deforms a little. Rock under Redwood Valley behaves like that when fluid pressure is high. The main fabric trends northwest, the right lateral direction. The conjugate cracks trend northeast, the left lateral direction. They meet at roughly 90 degrees and lock together. Fluid in pores can lift rock off itself if pressure climbs. Then a tiny stress gives a tiny slip on a tiny crack. That slip changes stress on the next crack over. That is why the 2020 dots did not line up neatly. They formed a cloud about 1 kilometer across, not a sharp line. The wider zone that hosts such clouds is 10 to 20 kilometers wide in map view. Not a knife edge, but a braided river of fractures. Elsewhere, the same mesh has been seen where fluids drive swarms. For example, Mammoth Mountain in 2014, a few hundred kilometers south. The rock there was not breaking a fence line. It was opening a network a little at a time. June 24 did the same, but with one piece large enough to feel across counties. A mesh matters less if the map is finished. This map is not finished. In 2021, a team flew LiDAR over the northern Maacama. Not photos, but light that strips trees away and shows bare ground at centimeter detail. The team that processed those strips and walked scarps was led by USGS geologist Charles Trexler, with collaborators from Humboldt State and Penn State. They found the northern Maacama is not one trace through Redwood Valley, but multiple strands. Some scarps are 2 to 4 meters high, taller than a person, sharp in hillshade. Some streams are deflected 50 to 150 meters where the fault has dragged them right. Many of those traces were not in the state database before LiDAR. They now splinter up through the valley floor in N-echelon steps. And the June 24, 5.6 did not hit dead on them. It hit just north of them, beyond the tip of the last solid line. That is exactly what you expect if the network continues farther north than anyone has drawn. The report line put it plainly that the quake will instigate the identification of yet more strands extending up Redwood Valley. The direct description of the zone written after the quake said the vast majority of strands have yet to be identified. In other words, the fault system is longer than the line we draw. The mesh is wider than the map. Tell someone that, and they will remember it. You might say 5.6 in the hills is small and far. San Francisco is more than 100 miles south, so why listen? 5.6 releases about as much energy as a single large quarry blast repeated a few times. Not a city killer on its own. The address matters more than the size. The Maacama runs under towns where people live, work, and send kids to school. Willits, Ukiah, and the Redwood Valley floor itself. South of there, the same system runs as Rogers Creek under Santa Rosa streets in its creek floodplain. New mapping shows the Rogers Creek Fault extends about 17 kilometers farther north than previously thought, flanking the east side of Healdsburg. That is not a line on a distant ridge. That is a line under a grocery store and a school. The plates do not care which name we gave the trace. They care how much slip is available and how long a break can run. The Bay Area hazard number includes that. There is a 72% chance of a magnitude 6.7 or greater somewhere in the region before 2043. That number counts known faults, lesser-known faults, and unknown faults. Unknown faults are in the math. The Maacama is exactly the kind of lesser-known fault that math is talking about. How often does the Maacama make a large quake? We do not know with the precision people want. That is not a dodge, it is the trench result. North of Willits at Hale Creek, geologists dug trenches across the fault and logged the layers. The careful work was carried by the USGS paleoseismic crew of Carol Prentice and colleagues who date Bay Area faults for a living. They dated charcoal, buried soils, and offset channels where Hale Creek has been shoved sideways. Fault terminations showed a surface rupturing quake between 1060 and 1180 calibrated years before present. Call that about 900 to 800 years ago. A folding event they attribute to another large quake happened between 790 and 1060 years ago. A buried channel that has been offset 4.6 meters is younger than about 560 to 690 years. Do the math and you get a long-term slip rate of 6.4 to 8.6 millimeters per year. That rate is higher than the 20-year creep rate of 5.7. The mismatch matters. It says creep alone does not account for all the motion at that site. Some motion must come as quakes. A trench 7 kilometers southeast suggested the most recent surface rupture after 1410 AD, but before 1660. If those two trenches record the same event, the window narrows to 1520 to 1660. Either way, the quiet spans centuries, not decades. No major historical quake has ever been tied directly to the Maacama. And the Holocene traces in this region are rather poorly known, which is why every LiDAR flight rewrites confidence. Partly creeping sounds safe, and partly it is. It bleeds off strain a little every day. That is why the Maacama can go decades producing only 4s. It also explains why the long-term hazard is easy to underestimate. A partly creeping fault can still store enough strain for a large rupture. The early assessment that guided Warm Springs Dam put a maximum credible quake on the Maacama at magnitude 7.5. That assumed about 150 kilometers going at once. Later deterministic work for a site in Ukiah used a 7.42 kilometers away as the controlling case. State shake maps use a 7.55 on the Maacama as one of 4 scenarios for Sonoma County. Those numbers assume the network can link. Does a mesh make that harder or easier? A mesh makes a long straight crack harder to grow, but it makes a jump across a step over easier if fluids are high and many strands are already close to failure. The 2020 mesh had 2 families of faults ready to go at right angles. June 24 lit a nearby strand after years of mapped strands stopping just short. The path for a larger rupture is not a single fence line. It is a set of closely spaced gates. If enough gates open together, you get length. Length is magnitude, and every extra 10 kilometers is more energy. Add the deep slip, and the plates show their math plainly. 21.5 on the San Andreas, plus 13.1 on the Maacama, plus 7.5 on the Bartlett Springs. That totals roughly 42 millimeters a year, an inch and 2/3. That is the budget north of San Pablo Bay. If the San Andreas took it all, you would see one fat line of strain. Global positioning shows it does not. Strain is smeared across 3 systems, and the Maacama takes about 1/3 at depth. At the surface, it leaks much of that as creep and tiny quakes, but not all. The difference between 13 at depth and 5.7 at the surface is the part that can load. Over a century, that difference is about 70 centimeters, more than 2 feet of slip waiting in elastic strain if nothing else gave. Geology at Hale Creek found 4.6 meters offset in about 600 years. That matches the arithmetic of deep slip minus creep. History and geodesy agree, even if history is sparse. The system is not slipping freely. It is storing slowly on a network that is wider than the line we draw. That is why a 5.6 cannot be read as a pressure release. It is a leak, not a drain. There is one more gap the maps now admit. Between Santa Rosa and Healdsburg, the Rogers Creek Fault was thought to end. LiDAR says it does not. A set of subtle traces now links the Rogers Creek zone eastward through Bennett Valley toward the southern Maacama. The connection was documented in the years after 2016 and published by 2019. That matters because length is magnitude. The Hayward-Rogers Creek Maacama corridor is about 275 kilometers if you count it as one system. That is San Francisco to past Willits as a single plate boundary at depth that steps sideways at the surface. Stepovers can stop a rupture cold. They can also be jumped if stress is high and fluids are present, which the mesh tells you they can be. The Maacama LiDAR work found sags and scarps in those stepover zones that were labeled uncertain before direct digging. Now they are mapped as certain and active. That change is not academic. Hazard maps move lines and building codes move with them. A house that was 50 meters from a dashed line can wake up 10 meters from a solid one. June 24 did not change code overnight. It changed confidence, and the confidence points north of the last solid line, where aftershocks clustered that first night. Leave the graphs for a minute and stand on Tomkey Road at dusk. The monastery bell has stopped and dogs bark far off. Air still smells of dust shaken off roofs during the morning jolt. Look at the ground, not the sky, and follow the low-pressure ridge just east of the road. It is only a few meters high, but it is straight for hundreds of meters. It is not a hill made by water. It is ground pushed up where 2 sides of a fault press together. Papers call that transpression because the plates do not slide cleanly there, they squeeze. North of San Francisco Bay, that squeeze lifts the coast ranges and makes lines of oak on a ridge and sag ponds in flats. Thrusts break out and add vertical lift to the steepest slopes. Downtown Willits at the same hour is different and familiar. Cars pass over the fault and you would not know until you look. A curb has a hairline offset and a shop window was reputtied last week after June 24 cracked it. The owner wipes dry wall dust off jam jars and says the shaking was short and sharp, not rolling like coast quakes he remembers. That snap matches hard Franciscan bedrock under Redwood Valley that delivers fast acceleration. Utility crews cut power to 5,600 homes, then got it to 4,400 by evening. A cracked toilet, books off shelves, pictures down, no collapsed highway. For a 5.6 under a town that could be called luck. Or it could be the mesh taking energy and spending it on many small cracks instead of one long tear. Does this mean the big one is coming? No. The big one people fear is a 7+ on the San Andreas near San Francisco. This was east of it, across the hills, on a different set of faults. That set splits the plate motion because the San Andreas alone does not take it all there. Aftershock math that first night gave only a 7% chance of a magnitude 5 or greater. The odds of a triggered Great Quake on the San Andreas 100 miles north are vanishingly small. That is the honest answer. Here is why it is not comforting. We have mapped only a fraction of the network, and the vast majority of strands have yet to be identified. Paleoseismic trenches say the last surface rupture was centuries ago, not years. Creep at 5.7 cannot close a long-term need of 9. The deficit hides in a mesh that can make a future rupture longer than the drawn line. The next time it moves, it will not ask whether our map is finished.